Assalamu alaikum. In this lecture, I'll talk about the energy in the presence of dielectric materials, and then I'll move to chapter 5, talk about magnetostatics. This is the work done to assemble a charge, which is given by half integration rho phi d3x. Now, if there is a charge dq in the presence of external field, then the work done is phi external times dq. The total work is you have to integrate over rho dv. If phi produced by the same source, then the work is given by this expression. If you push delta here, we get phi delta rho plus rho delta phi d tau. Then we have the same expression to assemble a charge in a certain position. Now, in the presence of dielectric, we have used the same relation delta rho. We are assembling delta rho. In this case, phi is already exist, and there is a change in delta rho. Now, using the divergence d equal 4 pi, the variation in delta rho is the variation, the divergence of d, which is given by this expression, and substitute here for delta rho, we get this expression. Then using this identity and convert this into a surface integral plus a volume integral, and then take this to the infinity. The surface is to the infinity. Phi is proportional to 1 over r, d is proportional to 1 over r square, and d a proportional to r square. The overall is proportional to 1 over r, which is 0 at infinity. We left with this expression, and this is over the whole space. Now, to apply the previous relation to a linear material, that's d equal epsilon times e. We have to substitute instead of delta d by epsilon. Epsilon now is constant times delta a. So we get this expression, which is 1 over 8 by integration e dot d d3x. It means that the work done is given by this, the integration over all space. The energy density is defined as 1 over 8 by e dot d. Now, for nonlinear materials, we have to integrate to this integration from 0 to d, the state of polarization. This is an example of ferroelectric materials. Now, for magnetostatics, we need divergence. The condition for that, we need divergence J equal 0. J is the current density. We already know that divergence B 0, and Beer's law is given by this. Curl B equal 4 pi over C equal J. In matter now of second equation, we have to replace B by H, the magnetic intensity, where B is the magnetic induction, and the relation between B and the magnetization in CGS system of units is given by this. Now, to calculate the magnetic induction at point P due to source I, we have to use Biot-Savart law in this case, and for I, instead of IDL, we have to, for distribution, write GS, the current density times ds. So we have for B 1 over C of this integration. This is called Biot-Savart law. Now, the force between two currents, here we have two loops, the first loop current I1 and the second current I2. We have to find the magnetic field of the second loop acting on I1, and then calculate the force using this relation I1 dl 1 over C cross B2, and then perform the integration. We get this relation. This can be simplified using backup rule, and noting that this thing is minus d over r 1 over t. So in this case, this integration over this one gives us 0, and substitute in the above equation, we finally reach to what's called the Newman equation. Here, this is an example, two infinite wires. The first one carrying current I1, the second carrying I2. the separation between the two wires d. So this is the force per unit length on each wire, which is given by 2I1 I2 over c square times d. You can use the above relation to find this. This is the form of F, and this is the form of the torque. The torque is X cross F. Here we have, for distribution J, we have to convert IDL into J3 D3X. Now let's prove that divergence B is 0. This is the Biot-Savart law. So we have to act by a divergence. This is n prime. So now using this relation, and note that the curl of the unprimed on J give us 0, and the first term is give also 0. So we finally get 0. Integration of 0 is 0. To get Laplace, to get Ampere's law, we have to take the curl of B. B is given by the Biot-Savart, as in this case. Now this quantity can be written as minus a gradient of 1 over x minus x prime. Then using this relation and noting that the second integration gives us 0, we finally get this relation, curl B equal this thing. Here we have to choose the gauge, divergence A equals 0. Now this curl B now can be written in this form. The Laplacian of this thing is gives us, if you push delta inside, we get minus 4 by delta x minus x prime. So this is the first term. The second term is this. Well, now we have to prove that this term is 0. We have to change. You have to use again this relation and change to the primed using this relation. We finally find this is equal to 0. We convert this using divergence theorem to surface integral, and this reduces to 0. This is curl B, which is 4 pi over C times J. This is Ampere's law. Now the magnetic vector potential. Now we have divergence B equals 0, and curl B is 4 pi over C times G. If J is 0, then curl B is 0. That means B is minus a gradient of some scalar potential phi m. Substitute in the divergence, we get Laplace square phi m equals 0. In this case, we have to solve Laplace equation. Now, if J not equal 0 does not equal to 0 when divergence B is 0, means that B can written as curl of A is the magnetic vector potential. Now substitute in the Ampere's law, we get this relation, which is the Poisson's equation in vector form. The solution of this is A, which is called the vector potential, equal 1 over Cj over x minus x prime d3x. That's it. Thank you.